Okay, let us go ahead and get going tonight. We have several fun things that we like to show you tonight and really build on what we've been working on in the past. We are going to go ahead and just kind of take that structural stuff we've been working on so far and hopefully kind of pull it all together in a cohesive way where we'll be looking at a building that has a lot of different structural elements, put into it in a fairly complete way. And we'll think about sort of this whole issue of how the structure and the facades and how that all sort of works together in terms of all those different layers and how those things actually get connected in the real world. We'll also take a look at the issue of foundations. And finally, we'll be looking at just really how we apply loads to the structure so we can take it over and do structural analysis on the rails and blah, blah, blah. Kind of like to continue with all that. And you can do that in a number of different tools. So if you are a big old fan of CSI, what's the name of the tool we all use here? Oh, we do structural engineering classes.
ETABS.
ETABS, thank you very much. It's funny, I too many programs. So if you're a fan of ETABS, you can take it over there. If you're a fan of some other programs, I can show you how to do the analysis on the web, just as a web service, or actually using another program that's available called Robot Structural. So a number of different options. So we want to go ahead and take a look at all those things in preparation for just continuing to move our structures along. We're going to, after this session, do is start shifting more into really the mechanical systems and kind of think about the air quality and how we actually model all those systems. But let's go ahead and finish up the issue of the structure, because I understand from the check-ins that there are some questions that are coming up, like from the crowd, and let's see if we can sort of address some of those. And along the way, please chime in. If your question's not being answered, throw your question in the mix. So we'll see if we can get it answered. Okay, to get going today, if you would like to follow along, head on out to coursework and pull down the session 10 starting point, which is an awful lot like the file we were working with last time, but I went ahead and flushed it out with a little bit more structural information. So if you can download that and bring it up to your machine, I will show you what it looks like. So at some level, it kind of looks like this. Let me go ahead and though expose the structure to you so you can actually see what it looks like. So for example, right now you're looking at the building skin, you're looking at some facades, you're looking at some columns and things like that, and the roof plane. If we actually want to go through and just sort of focus on the structure, it may be helpful actually just to go through and create a view that just focuses on that structure. And let's see how we can do that. For all the different views that we're creating, they have a number of different attributes that allow us to go through and change them. So for example, this view right now has all those things exposed. It actually has a discipline associated with it too. It's called a coordination view. Coordination views kind of show you everything. It'll show you the architecture elements, the electrical elements, the mechanical elements. The idea is you're supposed to see them all together and you can coordinate between them. But let's go ahead and change that up and let's see what we can see instead. What I'm going to do is take that 3D view and I'm going to just duplicate it because I actually want to keep the whole integrated 3D view together. I'm just going to duplicate that, and I'm going to rename that copy as just something, I'm going to call it 3D structure only. And don't have to do that. That's just going to make it a little bit easier as we move to kind of keep on popping into the structure. For that, what I'll do is actually change its discipline so it looks a little bit different. Let me just try changing the discipline to structural. And, well, some information disappeared in there. Sort of see the slabs. I can still see the curtain walls. They're still showing up in there. But I see a lot of the structural elements. Let me go ahead and take it one step further though, because these are all the elements that it considers to be related to structure. If I want to go through and take it one step further and only see the actual structural framing elements, I can then go through and do more like a visibility graphics thing. So under the View tab, there's this whole notion of visibility graphics, which lets us turn on and turn off different things. So we can turn off things like the curtain systems. Another way to approach it is we could actually sort of turn everything off and just turn back on the things that we want. But let me go ahead and turn off that roof right now. I'm even going to go ahead and turn off the floor right now, just so that I can only see just the framing elements. Okay. So that's the basic shell of the building as we've built it so far. You'll see that we have a couple of different framing systems at work here. We have down on the lower floor, I have some sort of steel-based system. You know, I have those kind of columns coming up, I have steel beams, I have some sort of joist system that's supporting the floor. Kind of a fairly standard sort of construction. Up at the roof, though, I've actually put a bit of a wooden system in there. I kind of like the idea of a big open space and maybe some nice big old blueland beams that are exposed in order to kind of see the architectural beauty of all that kind of on the inside. So I have just spanning from the back columns all the way to the front columns, these very long spans and these very deep beams. These beams are actually, they're placed just like the other beams. I just loaded in a family and chose a size. These are, what are they right now? 6 3/4 by 36 inches tall. So if you haven't seen blueland beams, they're actually really cool. What they do is they take just really layers of like 2x lumber and glue them all together to kind of make an incredibly tall stack. And blueland beams are very nice. They can span very long spans. You'll often see them used when you have a curving span, because it's actually, they can form them with all the different layers to go and just taper to follow any curve that you want to. So blueland beams are really, really nice. Then I've put some intermediate beams between there. Little wooden ones that are kind of hanging out, spanning between those that are actually going to support the roof plane. These little intermediate beams are actually parts of beam systems. So all these little guys down here, the steel K-bars, as well as these smaller beams, those are part of a beam system that has a very regular spacing. And if you want to, you can tab, kind of get the whole system. Then you can see it's made of these glue lambs, and currently they're at 8 feet. If it turns out later I need to make that 6 feet or 4 feet, whatever it is, I can apply and it'll change all the ones within that system. So beam systems are very nice in that they give you that ability to kind of change a whole system very, very quickly. So that's just sort of a starting point in terms of where we want to get going. I'm going to kind of talk ahead a little bit in terms of thinking about this building structurally. You know, if you look at the building in the way it's modeled right now, you do notice that there are things that look a little wonky right now. For example, if I come up here, you'll see that looks a little strange right now. Clearly something different is going to happen up there in terms of that final connection between that sloping beam, the beam coming in from the right, and this column coming together. Okay. But at least at a high level, in terms of modeling it very quickly and just sort of showing the graphics very quickly, this is sort of the way it's representing it. What it basically does is it stops the beam at that point where as soon as anything on it connects and overlaps the other element, it just stops. It doesn't try to resolve those things together. Again, we can try to do this thing called coping to go through and make those fit a little bit better. But what I want to show you today is that actually beneath all this structural framing, there's actually something called the analytical model, which I actually typically keep turned off because it's just kind of more graphical information you may not want to see. And that's what you actually need to see in terms of how it really understands analytically how this thing is going to fit together. So the analytical model, again, is typically hidden, or at least I have it turned off in the visibility graphics. If I want to see it, there's, again, these little widgets down at the bottom which control what is visible in the view. And the second one over from the right, you go ahead and click on that one. Kind of looks like a little light bulb in front of a little structure that has red lines on it. It'll actually turn on the analytical model. Okay, and in the analytical model, which will become important to us when we want to go through and do the analysis, okay, you can see that those beams do connect up there. We have the column line, we have the beam lines, the connecting in there. There's actually a connection there between all these things, and we can specify the qualities of that connection, which will be important when we actually go through and do the structural analysis. Is that sort of a simple pin connection? Is there some sort of resistance in 2 directions? Is it a moment? We have a connection that's going to resist in all 3 directions. So whatever's going to happen there, and we'll go through and specify those things. So there's always these 2 models on top of each other, the physical model and then the analytical model. And the analytical model is really the one that goes through and dominates from the standpoint of doing just the analytical, the final analysis. Now, if, for example, you want us to see the analytical model, not all the physical model, because you really want to focus on that aspect, we could again do something like duplicate this view. And duplicate that, hang that, turn that on. And in this one, I'll rename it. I'll say 3D and the analytical model. And then we can use our visibility graphics to go through and control that. So visibility graphics, again, it's either, I always type VG, but it's also VV, or if you go to the View tab, it's also available there. And within here, the analytical model categories are over here. I can say turn off the model categories. Okay, that'll turn off the physical model. And really, that's what it looks like analytically. And you know, if you're used to kind of hanging around in E-tabs, that may look sort of familiar to you. It's very, very similar to the types of models we went ahead and created over there. So you just know there's these different types of models that all work together. And yeah, ultimately, we're going to be applying loads to the physical and the analytical model. That's sort of applied in both places. And this will actually sort of determine, you know, on this big plane of the roof, really what's supporting it in the end and really what it's all connected to. So you know, don't get worried if somehow the physical model looks a little wonky. If the analytical model is correct, then you know, things are supported the way they need to be, and we can sort of clean up the physical model as need be to kind of make it look better. Okay, so I know there were some questions in the kind of discussion sessions in the check-ins with people about the whole notion of, well, really, you know, how do we decide on all these materials, and how do all these materials start working together? And let's kind of even almost open that up to more of a discussion, because it really is kind of a discussion and thinking about that in terms of sort of the materials of your framing system, and then really sort of how your framing system relates to your facade system, and how they all fit together. Because there's a lot of ways to go through and do that. And let me even, to kind of start it, go ahead and show you what I did in this model anyway. If I come back to the 3D model, I have a view called No Roof, or even the floor plans. Maybe that'll be a good way to show it to you. You'll see that in steel frame construction, very often the issue of the facade and the structure are actually somewhat separated. That what we often do is we take the facade and really just hang it on the floor, but the structure really almost stands independent of what's going on in the facade. And we can do that really when we're doing something like that. Let me go back to the just structure only, something like this. Yeah. We're basically saying that the frame, the structural framing here, the columns, the beams, it's really fully supporting the loads, at least the gravity loads. We'll talk about the lateral loads in just a minute. But all those gravity loads are really being carried down by the structural elements. We're not really depending upon any of the walls to go through and support those loads. And that's very common in a lot of commercial construction. It's the way that the Y2E2 building is constructed. A lot of buildings of any scale are really designed that way, so that the frame is really quite independent of the facade. And by doing that, you have a lot of independence. The frame or the facade can change very radically, and it really won't have any impact on the structural stability. So it's very common to kind of separate those things and really think about the facade as being the skin that just sort of supports things. Sort of like our human body, that our skin's not really supporting very much. It's kind of keeping everything inside, but it's just a skin on the outside. That's a very typical approach. But let me contrast that with about the only place where you get something very different is in light frame wood construction. Okay? But, well, concrete can be too. We'll talk about that also. Yeah, there are cases where we actually go through and instead of putting a lot of columns in explicitly, we just use the light frame wood walls to go through and support the loads. And if the loads are not so concentrated that they can be distributed nicely across the entire wall, super, that actually works. Yeah, there are times even in wood frame construction where we, I gotta illustrate this, maybe it'll be better. Let me build another little building right next to this, because I think it'll make more sense then. I'll take in a little building over here. Put it on level 1, just go up to level 2. That's fine. A little kind of rectangular thing. I don't have any stud walls in here. I could go ahead and make one in just a second. Instead of these metal studs, we can imagine those being wooden studs. But my graphics look funny. Oh, it's because I'm hiding those elements. Hang on. Let me turn the walls back on. There's always, no, that's not there. It's because it's, let me put back to coordination. I got some little walls there, little stud walls that are hanging around over there. I could go through and change them. Right now they're metal studs, but I could just as easily go through and make that wooden studs. They would have more structural stability. Metal studs tend not to have very much structural stability. Well, they have some. So on top of this, I could go through and add a framing system. For example, in a lot of residential construction, light frame residential construction, what they'll do is something like this. We'll create a beam system, but it'll be made of actually very small elements. So let me go ahead and load in something that would be appropriate. So I will insert, I will load a family, structural framing. I'll make it wood. I'll call it dimensional lumber. And for what I'm thinking of, a series of floor joists that would rest along those walls, a very common size might be 2 by 10 or 2 by 12, just some sort of relatively common size like that. So I'll grab some dimensional lumber. I'll get to grab the 2 by 10s and 2 by 12s. Super. And now I'll make a beam system. I'll say I'm going to make a beam system. It's going to be up at, let me put the level plane. I'm going to put it up at level 2. And then in terms of the system, it's going to be these little 2 by 12s. They're going to be every 16 inches or so. That's a very common spacing, maybe every 2 feet, depending on how they're framing it. And now I can go through and put that in. So I'll say, great. Put it on. I'm thinking about why it's not letting me do that. If it's not going to do that, I'll just put it up in here. Zoom to fit. Draw. Oh. Well, that's interesting. It's because of that. Okay. It's because there's no beam right there. It's actually a wall instead. Let's put them on the surface. So let's go back to 3D and I'll show you what that looks like. So this is kind of a very common way of framing things. In a lot of wood frame construction, we do something like this. And in this wood frame construction, the neat thing about it is if we have these joists spaced ever so closely, if it really is every 14 inches or every 24 inches, something like that, the amount of load that is coming down on individual space is not so great. So you can actually just, in the strength of the wall itself, carry that. We don't actually sort of go through and crush anything because there's really not that much load. Okay. So that works in light frame construction. Yeah. If it was a wooden wall, super. Yeah, we have a certain amount of spacing. If it was a concrete wall, even better, because the concrete walls are really a lot stronger than the wooden walls, so they can go ahead and handle that load. No problem at all. In fact, you see a lot of foundation walls. You know, what you'll do is we'll take some wall like this, and we'll just suppress that a little bit. Okay, so they're all sitting on top of that, and then this will be some sort of concrete wall. Or better yet, I can make it out of concrete. I should do that. So again, I will take that wall, let me edit its type, I will duplicate it. Put it over here, I'll make it concrete. Cast in place concrete, which will have some materials that can be analyzed. Okay, there is an interesting issue right here in all wall types you should know about. It's this notion of, is it a structural wall or is it not a structural wall? Walls by default aren't assumed to be structural. They're considered to be architectural, so they're not actually considered to carry loads. So if I put a load carrying element on a non-structural wall, it'll often warn us. It'll say, hey, you know, that thing's not really designed to carry loads. It's more of an architectural feature. If I want it to be considered structural and be considered part of the analysis, I just need to turn that on. And as soon as I do, we get all this information about the rebar and just really what the kind of a distance or what the resistance is going to be like. There's also this notion here of really, as we're going to be analyzing it, is it only considered for the bearing, for the gravity loads? Is it going to be considered in the shear calculations or some combination of both? Okay, so every wall element, you get to sort of specify that. So in terms of these exterior materials, you know, walls actually can go through and support things. Concrete's very, very good. It has a very high bearing capacity. Wood, not so much. If it gets to be, I think the limit is if you have like over 2,000 pounds coming on the end, and that seems very high. You basically have to make sure that it's not just sort of sitting on the wall. You have to explicitly put a post in the wall. So another very common thing we will do is, let's say instead of this, now let's say instead of this being like concrete, I'll put it back to more of a stud wall. Okay. If that stud wall doesn't have the bearing capacity, but we have an awful lot of load coming from any individual member, what you'll see on the plans is something that looks more like this. Zoom to fit. And what we'll actually do, and I'll do it in the ceiling plan, I can see a little bit better what's going on. We'll go through and put a structural column. So we'll say a column, but instead of a big old steel column, it'll be more, okay, structural column there, wood, dimensional lumber, and a very common, like in a lot of the work I do, we use 4x4s or 4x6 columns just to support beam loads that come on down. So we'll go through here, and in the framing, we'll put a structural column just right at the location where, zoom to fit, that is. So when I go back out to 3D, what you see if, for example, if I make this transparent, or I hide it, we kind of, oh. Yeah, you can sort of see that you tend to, at the place where there's the extreme load, we put a little extra support there because you don't want to crush the wall. So if you're thinking of a wood frame system or you're thinking of a wall system, super. You can go ahead and put that structural element right into the wall. And that's actually sort of a very common thing to do. Let's go back over to the other building though. I'm going to take a look at how we did it over there. Here I decided not to. I went ahead and just actually put the columns inside the building, holding them off about 2 feet. I have some idea of really how long the floor can extend without any structural support. You'll cantilever out a little bit and still be able to go through and support the walls right there. So you can do things like this. There are other systems, just so you know, that are sort of hybrids of all this. Like this system is basically saying that the structure and the wall are completely independent of each other. So I could really change that wall to glass immediately. It would have zero impact on the structure. Another way to do it, though, that some people will use is they'll take like a column like this, and what they'll do is, I'm going to copy it. They'll put it right in the wall like that. Okay. Typically what happens in a case like that, if it's right in the wall, that's fine. It's going to carry the loads on down, is, it's kind of in the stud layer. There's these outer layers, which are finish layers. We don't really want to poke through those. We want to kind of keep it back in the support. And what will happen here is in this stud layer, kind of right over here, you'll have that column that's kind of hanging in, hanging out. It's a little bit strange looking in terms of what's going on. What you'll do is go through and put in something that looks like this. We put some sort of interior partition in there. You'll get something that looks like, this. Okay, where it just boxes in around the column, stuff like that. Provides some fireproofing for the column, because we need to do that to kind of protect it from fires that might weaken it. And when you see things like that, that's actually something we call a pilaster. So it's just a column that's embedded in a wall. And in a lot of older construction, you find that in block wall construction, you find it in a lot of old masonry construction. You find these things where the beam's coming down on what looks like a column that's buried alive in the wall. Okay, there may be a steel column in there, it may just be sort of just a thickening of the wall surface itself. Okay, but that's what happens when they sort of come together on the wall. So you can, completely embedded in the wall, completely independent of the wall, or sort of halfway between. Okay, and it really just depends on how much flexibility you want. The difference is now that I have that pilaster there, okay, something like that,
if I want to go through and change that wall surface, what I'm going to have to do is just be a little bit careful about that. Maybe now, since it's there, if I don't want to expose that, I'm going to have to just sort of limit myself. So great, I can make U glass on that side. Okay, but I can't actually do it right at the piloster. It's just that little bit of thing about whether you want to see that structural skeleton from the outside or not. But that's kind of it. It's really not too much mystery to the whole thing. But let me ask you guys questions in terms of your cases and you guys in terms of what people are proposing. Like, what are some of the ways people are thinking about their structure versus the facade? Or, so do you have a sense of really where your facade is going to be relative to the structure? Like, how many people are sort of having a structure inside the facade? The spring, okay, got it. And other people in terms of having the structure in the walls itself? It can go either way. For the people who are doing the structure inside the facade, are you doing steel or concrete?
Concrete.
Okay. You like concrete. It's a good material. It's actually a very good material for what we're trying to do here. Steel or concrete? Steel? Yeah, very good. Yeah, concrete and steel, it's almost a funny choice, even if you think about it, in different parts of the world, concrete's incredibly common because steel is very, very expensive, concrete's relatively inexpensive, concrete has fantastic thermal properties, requires a little bit of quality control in the field. There's all these trade-offs in terms of what's going to go on there. It's just kind of often sort of local conditions and economics that sort of determine whether we go with a concrete or a steel building. How about for the framed buildings? The people are going to think about that. What do you kind of building your buildings at?
I actually have a question.
Yes.
How, or especially on the other building that
Yeah.
you
Oh yeah. Yeah.
the little square, how did you decide at what point to put the beam?
Ah, in terms of that like in terms of the column coming down?
Column, the supporting column.
Sure, no worries. Actually, this is a fake example now because this doesn't make any sense. What would happen here if it really was every 16 inches like this? I wouldn't need it because that 16 inches probably can be supported right on the wall. So here's very good question. Let me tell you how you sort of figure that out. If as you're framing, you end up with something like this. Okay, I'm hanging around over here. He's looking pretty good. Let me go ahead and load in another piece. It really all depends on kind of your framing system. Insert. Let me load in a piece in here. I'm going to bring in some sort of piece of dimensional lumber again, but a bigger one. So wood, some like 4x16. Okay, and the reason I'm bringing that in is what I'm trying to do is basically sort of say that there's going to be some piece of the structure that's a little bit different than the others. And the reason I typically have something like that is because, what I've done with my framing is I've set up something, that's just different. Maybe I have another beam, 4x16, something like that, that ties in over here because I have some sort of balcony, or I just have something that I've done that's a little bit different. So what's happening now is I have something going on where there's a lot of load that's being concentrated on a big old fat beam, okay? And it is transferring to another big old fat beam, and then the load that's actually coming to that point in the wall is really very concentrated, so it's probably going to get to be over the 2,000 feet, or pounds, excuse me. That's how you know where to put it. You basically put it in that spot where it's needed, okay? And that's all it is. So in the same sense, if there's one over here, I'm betting I'm going to need one over here too. Got to do that so that just wherever, and that's I guess the general rule, wherever there's a very concentrated load. Uniform loads every 16 inches, no problem. Heavy loads, boom. Okay, then you need a little bit of spot support.
So in general, if it's just a uniform system, you probably don't need any supporting columns.
Yeah, it really, actually, even so, we'll get to this today, it gets to really what the span of these things are. Because, let's say this was like 10 feet or something like that. Little off the, top of the head now. Okay, 10 feet long. Okay, let's say it's 40 pounds per square feet. Okay, live load. and they're 16 inches apart. Okay, so what I'll do is I'll take 40 times 1.3 times 10, that would be the total load. Okay, I divide it in half. I'd say half the loads go into this wall, half the loads go into that wall. Super. That number is, where we did it, 40 times 5, 200 times 1.3, 260, more or less. Okay, excellent. Things are looking good. Now, 20 feet, we'll get a little longer. 30, 30 feet, that much live load. Or if I space them every 24 inches, it's all just how much load you're accumulating. And as soon as you cross that threshold, actually 2,000 sounds off that, that's 1,000. Go look it up. As soon as you get higher than a certain level, what happens is, it's back to that shear thing that we talked about once. As soon as the shear gets so high that, these things are typically resting on like a little double wooden top plate. As soon as that shear gets so high that it would penetrate and go cutting through, then it's time to go ahead and put some support there. So that's the general rule. Okay. So in terms of like your facade systems, okay, so your concrete frame, let's talk about your facade. How's it hanging on the building?
The facade itself is going to be concrete walls and like a green wall hanging off of that.
Oh, beautiful. Okay, so there's some concrete on the concrete and then some sort of green wall. Perfect. Okay, excellent. Other facade systems? What sort of other facades are people thinking about? Yes.
Adobe and
What's that?
Adobe and compressor.
Very good. Now Adobe is going to get a really big, heavy material. Okay, so are you building on top of a concrete frame, or is that going to be just right on down to the earth?
I was gonna do it right down here. I was planning on having like a double Adobe wall, so like one that's more structural and one that's like the facade, and that way you can also get the insulation.
Got it?
Planning on just doing like wood framing within the Adobe.
Okay. Well, think about that. We should do some looking up about Adobe in this area in terms of whether we need to have kind of another structural frame inside. So I'm not sure what with Adobe, we can sort of get some sort of hybrid, whether it's pure earth or whether we actually put some concrete or something in there and then cover it with Adobe to because that's actually one of the rough ones is that Adobe typically is not very good for like lateral resistance. Although there was some really interesting research a couple of years or that engineers for sustainable world were doing like with Peruvian schools where they were kind of reinforcing Adobe to kind of really make it, because they have a lot of schoolhouses in an earthquake-prone area, and unreinforced tends to shatter. That's really catastrophic. So it was, there's ways of kind of reinforcing older ones to kind of add a little strength to resist that. It's great for gravity loads, it's just the last thing. Other facade systems? Anything else interesting? Anyone just doing a lot of glass? Or like some sort of panel system? Like Y2E2, like you have a sense of how you see all that stone on the outside of Y2E2 and it kind of looks like the quad, but it isn't. It just kind of looks that way. Do you have a sense of were you watching the new building getting built when they were building the new lab next door, how the panels actually came together? You have a sense of that? They basically hang off the frame. It's really kind of interesting. What they did, and let me kind of show it in the kind of the bigger building over here. There's a couple sections, let's say front to back. Let's see if I can kind of zoom on in here and we can kind of show you an example of what that might look like. So you got some sort of steel element that's kind of hanging around in here. Let me just kind of, we'll turn down those fat lines so they don't look so annoying. A little messy in terms of my detail, but I have some sort of steel and I have some sort of deck on top of that. Okay, this is supposedly the stud coming up. Maybe I should color that so it looks a little bit better. Just kind of a stud layer here. The stud's actually, this is an example of, this is currently an EIFS system. So there's metal studs, there's layers of foam, there's a little bit of sheathing to resist lateral, and then there's this exterior surface, which is kind of stucco-y covered foam. But really, these guys really aren't providing very much. The studs are really just there to provide backing for the wall. So what happens is, all these panels, okay, really just get clipped onto the frame. It sounds kind of strange, but that's how actually like Y2E2 and the building next door are put in there. So what happens in that sort of scenario is, let me just try to draw a big old kind of detail line to give you a sense of what it looks like. Make a nice fat line. What happens is, right over here, where that panel is going to come down, there's actually this funny little clip they put in place. So it's bolted to the floor, it's also bolted to the wall, and really the wall just hangs off of the frame. Okay. Same thing down at the bottom, there's going to be some little clip where through that little clip there's going to be bolts coming through, or studs of some type that are attaching that to it. And it's also going to be kind of attached to the floor, like right in here. Okay. And that's how it is. It really just hangs on the side. And that's really where we get the whole notion of a curtain wall. It really just is a panelized system that hangs. So even though as you look at the Y2E2 building, or any of the buildings in the SEQ here, they look like they're all these stone panels. It's really this precast panel. It has this limestone, very thin layers of limestone attached to the outside. But they're really just trucked in as panel and just sort of stacked up on the building, and some guy comes by and it is bolted into the frame of the building. And it's really just all carried by the floor. So there's really no load coming down to the walls, which is kind of interesting. So, you know, why they do that? That facade system, it just gives you just an awful lot of independence. That stone, they didn't have to engineer the stone and everything inside of it to go ahead and carry the loads. Yeah, it's just really more a facade. In fact, there's some really interesting places where they're joining them together, where you can see where the stone kind of, it comes together. See if you can spot the joints where, you know, like one, it looks like sort of brick, like the stone is interlocked with the other, and you can spot the joints where the panels actually came together, and there's actually just an expansion, you know, compound in there, you know, that sort of gives it that appearance, but it actually, you know, isn't like a big solid stacked stone building. Yeah. Some people complain and say that's really kind of fakey. You know, it's like not really very true to the material. But, you know, that's for the architects to debate in terms of really how good that is. You know, but yeah, that's really what it went to. So for your building, think about that. Once you get the structure there, you have an awful lot of flexibility for the facade. So if you put the structure in there, if you want to do a section of glass bottle facade, and you want to have a section of adobe facade, and you want to have just really interesting, weird things happening in your facade to demonstrate different features, hey, okay, because the structural frame is going to handle it independently. So, yeah, it's such a kind of, you have some freedom and independence. Okay, other questions about the file? Let's kind of think about that, because it is kind of a big one. This whole notion of really how your frame and your facade get together, and whether you're carrying loads through the facade, or whether you're just carrying them through the frame and the facade's just a skin. Does that make sense? Okay, great.